right, let's run through another chemistry question. This one says, what is the oxidation state of the bold element in each compound below? So oxidation state is going to refer to the charge, basically, on the atoms in each one of these compounds. So we have to figure out the charges on the individual atoms. So here's a periodic table with oxidation states of each period labeled. The left side of the periodic table is going to have positive charges, and the right side will have negative charges, and the noble gases have no charge because they have a full octet. Their outer shell is full of electrons. So the left side of the periodic table has a couple electrons that they want to give away to have a full shell, and the right side of the periodic table wants to grab a couple more electrons, which will give it a negative charge to fill their octet. So chlorine is one column away from the noble gases, so it has a charge of -1. So we've got Cl2 with a -1 charge. There's two chlorines with each having a -1 charge, and then we got Fe, which is iron, and that's a transition metal, so it can have different charges depending on the situation. But since we know there are two chlorines at a -1 charge, the total charge on the chlorines is -2 because there are two of them. So to balance that out, to make this a balanced compound with a charge of 0, one iron would have to have a +2 charge. So the oxidation state of iron is +2. So that's how that works. We have to balance this out to have a 0 charge, and we'll kind of figure that out as we go. So in the next element, we've got two sodiums. Sodiums are in the first period and have a +1 charge. So in total, that's +2. Then we're wondering about the sulfur and the oxygen. Three of those, and oxygen typically has a -2 charge. So sodiums are +2 total. And then we have oxygen, which is -2 times +3, so that's -6. If we add those two together, -6 plus +2 is -4. But in order to balance that out, the sulfur has to have a charge of +4. So this one is +4. Again, we have to make these add to 0, and that's how we would make that work. All right, so in C, we have a situation, it's a little bit different. So typically oxygen has a -2 charge, unless there's some exceptions where that doesn't happen. I believe this is going to be one of those exceptions, because hydrogen is always going to have a +1 charge, and there are two of them. So if there's two oxygens, and we want to balance that out, the charges on the hydrogens are going to be +2. So oxygen is going to have to have the opposite charge of hydrogen. It's going to have to be -1 in this specific instance, because there are two hydrogens, two oxygens. If we want to balance this molecule, these are both going to have the same charge. Hydrogen always has a +1 charge. So this is an instance where oxygen is acting differently, and that's pretty specific to oxygen. Most of the time, it depends on what period you're in, but oxygen can be kind of funky sometimes. And in this instance, it's going to be -1. For example, in H2O, which hopefully most of you know is water, then hydrogen's always going to be +1. So here oxygen is, as it usually is, -2. This is hydrogen peroxide. H2O2 is hydrogen peroxide, and it's just oxygen acts a little bit differently in this situation, and it can occasionally. But typically, you can look at the period and assume that it's -2. All right, then we've got another pretty complicated compound down here. So we're looking at sodium, which again is always +1. There's 3 of those. Then we've got phosphorus, which we're wondering about, and then 4 oxygens. Let's say those are -2 each. So we got +3 from the phosphorus. We got -8 total from the oxygen. So our total charge so far is -5. So to counterbalance that, phosphorus must be +5. And that's how you find the oxidation states of elements in specific compounds.